So it is isomorphous. Yesterday we
Completely
have
soluble in both liquid and solid phases, sir.
completely soluble in both liquid and
In
solid.
solid phases.
Yes. So other student, I hope all of you have remembered that we have discussed this yesterday, right? What is isomorphous and what is that? So yes. So here in binary, when we discuss about binary phase diagram, in one phase we have discussed that if two component system that can be classified in how much extent they are mutually solid soluble. Okay. So if two component, yeah, if they are completely soluble in both liquid and solid phases, they are known as isomorphous system. Okay. And some other part, in another phase, they are not completely soluble in both the phases. They may soluble in liquid phase, but there is some limitation in solubility. So when they are when we discuss about solid state. Okay. So if component is completely soluble in both liquid and solid phases, we will call it as a isomorphous system. Example of its here, if you can see the phase diagram or this diagram here, how the phase diagram has drawn and their corresponding microstructural changes. See, in microstructural way, their structure change. Their structure change. That's why they changes their form from suppose liquid to gaseous or solid to liquid like this, converted from one phase to another. So here, if you can see in x direction, we have composition, right? From 0 to its composition has been increases, and in y direction it is temperature has been provided. So suppose this in such point, this is started at L plus before giving the temperature. Okay, in a simple metal, think that it is a simple solid metal. So now its phase will be like this. This phase is up to, and you are giving temperature. You are heating that component. Okay, when you heat and after reaching the melting point, it will start liquidification. But at the beginning, what happened? All the metal, all the component are not instantly get liquid, instantly not from liquidous phase. So slowly from solid, it will become liquid, right? So at the beginning, it will be solid. So it is written as S or solid, and then when you increase the temperature, when you increase the temperature at this point, you can say this melting point, it will start liquidification. But all the component, all the part of that component will not get liquid at that very instant. It will take some time. So till then, it will be in this phase. Here you will find liquid plus solid. Both the phase of that material you will find here. That's why it is written L plus S. Okay, L plus S. Then when all the material, all the component get liquidified, then there will be only liquid phase like this. Only liquid phase. There will be no solid yet. So okay. So here up to this some point has been given. Solidus point is this adheres to D and B. Okay, the DB. This phase below this line, if you can see the graph. Below this graph, all the component are solidus. That's why it is written solidus A dash, T and B dash. Okay, and then uh, after this line, after this upper line of this graph, all the part are liquidious. That's why it is written A dash, B and capital B dash. So this is written as a liquidious because upper of this phase, upper of this line, all the phase are in liquid form. And what happened in the middle? In the middle, you will find both liquid state as well as solid state in this phase. Okay. So also as it is written that an isomorphous system, phase diagram and corresponding microstructural changes. So why it is again? Why it is in isomorphous system? Because if you can see, all the material can get solidified. Sorry, solid metal can get liquefied. And again, if you decrease the temperature, see at the beginning we are increasing the temperature, and from solid state we form to liquid state, liquidous form, right? And again, if you decreasing the temperature, if you reduce the temperature slowly, then again that liquid form, it will again, from liquid form it will again come to liquid plus solid state, because after some point it will get solidified, but at that moment all the material will not get solidified at that very instant. Some liquid part will be there. So at this phase, all the material, it may be liquid or it may be solid, but below this line it will again form the solid state. Okay. So here as in isomorphous, you know that, again I am repeating, completely soluble in both liquid and solid phases. Completely soluble in both liquid and solid phases. So you can see all the material completely it gets solidified, also it get liquidified. Both the phases, both the component it get, it can transform fully in liquid, solid phase as well as liquid phase. That's why it is written as isomorphous binary system. Why binary? Again, why binary? What is binary phase diagram? If a system consists of two components, equilibrium phase exists is depicted by binary phase diagram. So two phase solid liquid, both the phases are there. So now how the macrostructural structure or microstructure changes. So here, suppose at the liquid state, you can see its microstructure will be like this. If you take any liquidous form and if you check the space and under any microscope, you will find that its microstructure will be like this, very much distributed, no solid, small particle, it get distributed throughout its area, correct? And when this liquidified or liquidous material is get you reduce the temperature, then it will form, it will start forming solid phase. So at that time, in the means in this, in between these two lines, this graph, in this phase you can see that there are solid phase microstructure as well as liquid phase microstructure, both is present here. So with that red circle, it is means there is solid structure. Okay, and it's blue ink, it is indicate it is in liquid structure, liquid phase. Okay, so that liquid particle, they get solidified gradually one by one, and strong bonding start creating here. You can see in the middle part. Okay, so solid phase get created, and ultimately when all the material get solidified, the component gets solidified, then you will find a solid structure, a strong bonding with each other. Here in the liquid phase, you can see there is no bonding from one uh, component to another, one particle to another. But here, if you can see, a solid bond is formed between the particle. Okay? So here you can see that how this liquid to liquid plus solid, then solid transformation is happening, and also how their microstructure has been changed due to the phase changes. So this is important. This is important diagram we can put for isomorphous binary system. Okay. So all of you draw this isomorphous binary system. Hello students.
Hello, sir.
Yes. Please draw this.
Okay, sir.
You can see the screen, right?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Okay, draw this. Quickly draw that diagram and clearly mention the phases, that liquid plus solid, and solid. And here it is liquidious and solidus. Mention that, and also simply draw the microstructure. So we have seen that isomorphous binary system. So now, if in your exam, if we ask you what is isomorphous binary system, then you should write down the definition with and also with this diagram you can show how a isomorphous system, isomorphous phase diagram will look like. Okay, and at that time you can indicate these microstructural changes, then it will be great to see. Okay, so let's okay, 1 minute. Okay, so now we will see about what is cooling curve. Okay, and how that cooling curve is. So what is cooling curve? A cooling curve is a line graph that represents the change of phase of matter, typically from a gas to a solid or a liquid to a solid, where the independent variable which is uh, which is denoted in x-axis is time, and dependent variable which is denoted by y-axis or which is represented in y-axis is temperature. Okay. So what is a cooling curve? A cooling curve is a line graph. Remember that cooling curve is a line graph through which you can represent how a matter phase is changes. What is matter phase? Suppose you know that there is three type of phase like solid, liquid, and gaseous. Then so through cooling curve, it is a line graph through which the changes of phase, or you can say phase changes, you can denote, you can understand. Right? Line graph, that cooling curve represents the change of phases of matter, any matter. Okay. So typically, suppose from a phase changes means from gas to a solid or liquid to a solid. Like here, one line curve is denoted here, shown here. So here, there is two type of variable are there: independent variable and dependent variable. So this time, which is placed in x-axis, So it is that time is independent variable. It is not depend on any other thing. Okay, so time is independent variable. Okay, and the temperature, which is denoted in y through y-axis. This is temperature. It is dependent variable. What we understood with this cooling curve? Here you can say here this is was a matter phase changes diagram. So here is below sorry this point, this red line is known as cooling curve, where at this starting point it getting liquidified, okay, and up to this it is liquid phase. So from this point to this point it will start getting solidified, and at this freezing point all the liquid metal it get solid. Okay, so through this line what we have understood that how the phases are changes, like from liquid to solid. One example only given here, from liquid to solid, and like this way using cooling curve you can uh, find out how the phases has been changed. Like here liquid to solid, or it may be liquid to gaseous, or you can say gaseous to liquid. Okay. So if you increase the time and if you are decreasing the temperature, we are going below, right? So you are increasing the time and you are decreasing the temperature. So more you decrease the reduce the temperature, it will become that liquid material up to this, it will be in liquid phase. And more you reduce the temperature and give some time. After some time, all the liquid material get solidified. That's why that point, that point is known as freezing point. Freezing point means at that point, solidification has been started. From liquid to solid, it's get started, and from this point to this point, all the liquid material it gets solidified. So at this point, the complete solid phase you will obtain. Here, completely it is up to this, completely it is liquid phase, and at this point means at this line means it is freezing point. So at this point, liquid phase or this duration you can say, all the liquid phase it get converted to solid phase. So up to this, and after this point, follow my cursor. Up to this point, all the material are in solid state. Yeah, so this is known as cooling curve. Under equilibrium conditions, all metals exhibit a definite melting or freezing point. If a cooling curve is plotted for a pure metal, it will show a horizontal line at the melting or freezing temperature. See, it is the cooling curve shown here. It is for a pure material. So if your material is not fully pure, if there's some uh, ingredients, some chemical reagents, or some other elements are present, then it will not follow the straight line. Okay, that liquid phase it will not completely follow the solid phase. Okay. So this cooling curve is shown for a pure material. Okay. So if it is not pure, then this here you can see that straight line. It will not be a straight horizontal line. There will be some disturbance in there, or you can say because it will not follow the straight theory, because due to different components, due to particles present, if that material is not pure. Okay, that's why it is written under equilibrium conditions, all metals exhibit a definite melting or freezing point. So, if it is in equilibrium condition, all the materials it shows a specific melting or freezing point like this. Here, suppose at this point melting has been started. Suppose this point melting has been started, and you can see a definite freezing point, a specific freezing point. Okay, and this can be possible in and this can be possible in equilibrium conditions only. And for a cooling curve is plotted for a pure metal, it will show a horizontal line at the melting and freezing temperature. If it is not pure metal, it will not be a, it will not follow a horizontal line, it will not follow a straight line. You may find some curve, some other trend. So we understood what is cooling curve. A cooling curve is a line graph that represents the change of phase of matter, typically from a gas to a solid, or it may be liquid to a solid. Here, two type of variable are available. One is independent variable, which is noted in x-axis, which is time, and dependent variable, which is noted in y-axis, which is temperature. So another example has been shown here, like cooling curve for a pure metal during casting. I hope all of you know what is casting, right? Anyone? Any of you please tell me what you understand by casting. What is casting? Hello students. What is casting? What do you know about casting? Students?
सर वो मोल्ड करना होता है उसको लिक्विड को।
हाँ, तो क्या प्रोसेस है? तो प्रोसेस क्या क्या है? बताओ जो भी whatever you know, tell me. No need to think much. Just tell. Just express yourself. What do you understand by casting? Hurry up, hurry up. Anyone? Abhishek, Amit, Deepali, Kabir, Sandarbh, Kaushik. Anyone? What is casting? What happened in casting? No response?
Hello, sir.
Yes, tell me.
It is a manufacturing process in which a liquid material is usually poured into a mold.
Yes. And after that?
That's all, sir.
Which contain a hollow cavity of described shape and allow the solidify.
See, if I ask you people something, don't just search in Google and don't just reply. Whatever you know in your own language, you can reply me. Okay. Just tell me what you understand. Because MP1 you have gone through already. Right? MP1 cover हो गया ना? MP1. Hello. Hello. Students. Anybody? What is casting? So casting is as somebody told that it is a metal forming process, or you can say manufacturing process, where what we do, we pour the molten metal into a die. So what is the die? Die is the, you can say, replica of your what product you want to make, what component you want to make, and we pour that molten metal in that die cavity, Die means in there will be a cavity. Cavity, it will be a impression of your product. So when you pour that molten metal in that cavity, the molten metal, when it gets cooled, we kept it for some time so that that molten metal gets solidified. When that molten metal gets solidified, we'll break the mold, or sometimes we'll take out the solidified part. Sometimes we will break the mold, or sometimes we'll just take out or that solidified product, and in that solidified product you will find that the exact product which you want to make, it is there, because due to the negative impression on your die. So after some secondary operation, like after some finishing, grinding, etc., after we do that, then we will find our exact product. So that is the casting. So why we are showing here that casting cooling curve for a pure metal during casting? Because in during casting you can see that first we need to have our solid material, and then that solid material we need to melt. Okay, and then we melt means we will make it as a completely liquid. So that liquid phase material or liquid material we need to pour, and then give it some time to get again solidified. So due to the liquid, from liquid to solidification, due to this we are showing cooling curve for a pure metal during casting. So here again independent variable which is time, which is kept in x-axis. Then dependent variable which is temperature, it is kept in y-axis. And you can see here in that curve that first this pouring temperature means liquid material we poured here, and after that liquid cooling means we completely pour it in our die cavity. When you pour, then slowly it will get solidified, which cooling has been started. When you melted the material, then you need to increase the temperature. After that, when you pour that material into the die cavity, means what? You are reducing the temperature. You are giving some time to get temperature get reduced. So at that time you will find this type of, if you see its cooling curve with the reducing the temperature, you can see a downward graph. It is known as liquid cooling, means that liquid material you are cooling it, you are reducing the temperature. After sufficient decreasing the temperature, the freezing will start. Freezing will start means that liquid material start solidifying. Okay, solidifying is started. Freezing, it is written freezing begins. So this is your freezing point or freezing temperature. So we kept it for some time, then it will go through some local solidification time. As from the name itself you can understand that at this point, at this duration, the liquid material it get solidified. It gets some time to get solidified. So during this local solidification time, that liquid material will completely get solidified, and at that point all the liquid material it gets solidified. So freezing completed. This is total solidification time, and from the time when we pour the material, actually from that time solidification started, but actual solidification start at this point, freezing point. Let's say it is written local solidification time, and the total time from pouring the material to freezing completed, a total time period can say as a local total solidification time. Okay, and then when freezing is more completed, then still you reduce the temperature, then solid cooling means the the temperature which is still there in the metal. Okay, so that temperature will also get reduced, and slowly that metal will come in the room temperature. When it come into following the solid cooling, and it will come to the room temperature, then you can take out the material or pure metal. So this is a cooling curve for a pure metal during casting. So all of you understood this? Anyone having any doubt in this graph? So all of you draw this graph and point out all these points: pouring temperature, liquid cooling, freezing begins, local solidification time, total solidification time, then freezing completed, freezing temperature, solid cooling. All this you mentioned. So quickly draw this graph, and in the exam, see this type of question may come, that suppose draw the cooling curve for a pure metal during any manufacturing operation. So that time you can draw this. So all of you draw this. So we'll now we'll go next point. Okay. Next important point is polymorphism. Okay. So what is polymorphism? Polymorphism is like many substances, many components. Okay. These exist in more than one stable crystalline form. More than one crystalline form it is exist. It is, you can find out. Okay. So the various forms have the same compositions but different crystal structure. Like if you can say, if you take an example of water, or you can say pure, any pure metal. Let's take an example of water. So if you see that there is three phases are available: liquid, or solid ice, and gaseous vapor. Okay, three forms is available. So, but if you check the composition, you will find that composition is same, but their crystal structure is different. Means their structure is different, and also when it is water, it is in different form. When you will convert it into ice, it will be again different form. Again, in vapor, it will be in different form. So the various forms have the same composition but different crystal structure. Like water is having, it is found in different form, but their composition will be the same. Only that the crystal structure will be different. So change in crystal structure is observed due to either change in pressure or temperature, or both. So from ice, if you give the temperature, if you give some pressure, then it will form into water. So here the crystal structure has been changed, and by applying pressure or temperature. Okay. So it is written here: change in crystal structure is observed due to either change in pressure or temperature, or both. So that changes, like here from ice to water, that crystal structure has been changed. So this changing structure, such a change of structure is called polymorphism. Such change of structure is called polymorphism. Polymorphism is observed in pure elements as well as in chemical compounds, both inorganic and organic. So here, with the example I have shown you that how this crystal structure has been changed. So that changes. That change of structure, it is known as polymorphism. Okay. So now what is again, quickly again repeat. Many substances exist in more than one stable crystalline form. The various forms have the same composition but different crystal structures. Change in crystal structure is observed due to either change in pressure or temperature or both. So such a change of the structure is called polymorphism. Okay. So these crystal structure changes is known as polymorphism. So polymorphism you can find in pure material as well as in other chemical compounds that may be organic or inorganic. Okay. So this is polymorphism, and okay, let go through that next point. Eutectic system. So what is eutectic system? A eutectic system is a homogeneous mixture of substances that melts or solidifies at a single temperature that is lower than melting point of the constituents. A eutectic system is a homogeneous mixture of substances that melts or solidifies at a single temperature that is lower than melting point of the constituents. The coordinates defining a eutectic point on a phase diagram are the eutectic percentage ratio and the eutectic temperature. Okay. So what is eutectic system? Eutectic system is a homogeneous mixture of substances that melts or solidifies at a single temperature, and that temperature is lower than melting point of the constituents. Okay, so that is a eutectic system. So more we will one through more we will read about this eutectic system, then you will get more clear idea about this. So now what is homogeneous? Here we have written that homogeneous mixture. So now what is homogeneous mixture or what is homogeneous? Anybody? What is homogeneous mixture? क्या है homogeneous mixture क्या है? Anybody? Anyone? What do you understand by homogeneous mixture? Tell me. So homogeneous mixture or homogeneous means actually all are same, you can say. So homogeneous mixture is obviously it is a mixture where the composition is uniform throughout the mixture. From anywhere you take some component from a homogeneous mixture, the component. But if you do the chemical composition testing, what are the components you will find in which ratio? You will find that the same ratio if you take from another part, another homogeneous mixture. Okay. So homogeneous mixture means here in that mixture the composition is uniform throughout the mixture. A homogeneous mixture is a mixture in which the composition is uniform throughout the mixture. Okay, so here if you check solution, okay, if you talk about a solution, uh, in all solutions they are homogeneous because the dissolved material is present in the same amount throughout the solution. Whatever the material is dissolved there, it is present in the same amount throughout its solution. Okay. So today we discuss about different things like morphism, polymorphism, then uh, this cooling curve, specifically how this cooling curve can be drawn, and we have given an example of cooling curve for a pure metal during casting operation. Then we have discussed about polymorphy eutectic system. So in the next class will check more detail about eutectic system. Okay. So if any student having any question, you can ask, or if you have any doubt, you can clear it by asking me. Students, if you have any doubt, you can ask. Anyone having any doubt? So I guess we have understood the things. Okay. So now all of you please write down your